The title of my lecture tonight is From Equation to Superconductors, and the subtitle is Material under Pressure. So I'm going to discuss how to calculate or study or predict or even design of physical properties of superconductors, especially under extreme conditions and high pressure, without referring to the experimental data. Okay, so as I heard that there are no experts of superconductivity in the audience, so I'd like to start with a very brief introduction to superconductivity. And I would like to start with a story of swimming, Leo Leoni, and which was translated by Japanese famous poet Shuntaro Tanigawa. And in fact, in Japan, elementary school students read this story to learn the importance of teamwork or courage or creativity. And the story is the following. So the swimmy is a small blackfish, clever fish. And one day, this big fish, the shark, attacked Swimmy and his friends. And unfortunately, Swimmy lost his friends. And then he found new friends in the sea. And he taught the new friends to swim together like one big fish. And he became this eye of this big fish, and they stayed safe in the sea. And from this picture, we can see that the small fish is weak. But if the many small fish move together and move coherently, and then a very new and different situation is realized. And this is the so-called emergent phenomena. And in fact, this kind of emergent phenomena can be quite often observed in quantum materials. And the superconductivity is one of the most fascinating quantum emergent phenomena. In normal metal, in normal metal, electrons moves randomly and scattered by defects or impurities, and that makes a resistance in electronic transport. But in superconductors, at sufficiently low temperatures, electrons form the pair, which is called the Cooper pair. And those pairs, the billions of pairs, move together coherently. And in such a situation, the resistance becomes zero. So this is a plot of resistivity as a function of temperature. And in the case of normal metal, like copper or silver or gold, when the temperature becomes lower and lower, then the resistivity becomes smaller and smaller. And in an ideal situation, without any impurities or defects and so on, and then in the limit of zero temperature, this resistivity becomes infinitesimally small. On the other hand, in the case of superconductor, resistivity suddenly becomes zero at some temperature. So this temperature is called critical temperature, Tc, or superconducting transition temperature, below which the resistivity is exactly zero. And we can observe interesting phenomena such as the Meissner effect, perfect diamagnetization. And so this is a plot of transition temperature, Tc, of a variety of superconductors. And there are a variety of superconductors. The variety of superconductors have been discovered or synthesized since the seminal discovery of superconductivity in elemental mercury by Cameron-Ones. And so in this plot, so one interesting point is that sometimes if we apply extremely high pressure, then materials can exhibit superconductivity at very high temperature. So hydride superconductor is a famous example. And a more recent example is nickelate superconductors. So in these superconductors, if we apply extremely high pressure, then superconductivity appears at very high temperatures. And this phenomena is very interesting, but under extremely high pressure, sometimes experimental measurements become very difficult. And in such a situation, the role of theoretical calculation becomes very important, and to understand the physical properties of superconductors, or even predict or design of new superconductors. So it is important to study superconductivity theoretically based on equations. So next I'm going to explain how to study superconductivity from equations. Okay, so regarding the mechanism of superconductivity, actually a variety of mechanisms or scenarios have been proposed. But one of the most established and standard mechanism is that based on electron-phonon coupling. And the phonon is the vibration of atoms in the materials. And this was formulated by Bardeen and Cooper and Schrieffer. So this is a famous BCS theory. And in these phonon mechanisms, the superconductivity appears by the following steps. So in materials, there are negatively charged electrons and the positively charged ions. And the ions make the crystal structure. And when electron moves in materials, and then that induces a distortion of the crystal structure of ions. And then positively charged area is formed. And then another electron, this one, is attracted to this positively charged region. So effectively, phonons made it. So there is an effective attractive interaction between these two electrons, so mediated by phonons. And then electrons can make pairs, the so-called Cooper pairs. And as I mentioned, when the billions of pairs move together coherently, then a superconducting state is realized. So this is the scenario of BCS mechanism. And in fact, this superconducting state is fragile. And in the phase diagram, there are important three limits. So one is the temperature, so critical temperature. So at high temperature, superconductivity is destroyed. And also, if we applied a strong magnetic field, and then again, superconductivity will be destroyed. And also, if we introduce too strong current in the system, then superconductivity cannot survive. So there are three important limits: critical temperature, critical magnetic field, and critical current density. And superconducting state can exist only in these regions. And the physical properties of this superconducting state and the phase diagram set, so the three limits, can be discussed by the equations. So by the framework of the so-called Ginzburg-Landau theory. So let me explain the basic idea of this Ginzburg-Landau theory. So in this Ginzburg-Landau theory, first we introduce the order parameter of superconductivity. So the order parameter of psi r. Roughly speaking, it is a local density of superconducting pairs. So it is finite in superconducting state, but it is zero in a normal state. It is a complex number. So we have the phase, phi. And this is the source, represents the source of quantum coherence of superconductivity. And in the Ginzburg-Landau theory, we introduce a Ginzburg-Landau free energy, assuming that this order parameter is very small. So we consider to expand the free energy with respect to this order parameter. So there are several terms. So first is the free energy of the normal state. And then we have a second order and the fourth order terms to describe the second order phase transition between normal state and superconducting state. So in a normal state, at sufficiently high temperature, the coefficient A and B, these are positive. So if we plot free energy as a function of psi, then it takes the minimum at psi equals 0. That means the system is in a normal state. But when the temperature becomes lower, and then the sign of A changes. And then if we plot free energy, in this case, when an A is negative, then the free energy takes the minimum at finite psi. So this represents the system becomes a superconductor. And we also have the gradient terms, which represent the energy cost when we introduce the modulation in the psi, in real space. And the last term is the energy of the magnetic field. And in fact, starting with this free energy, we can explain a variety of interesting physical phenomena in superconducting states. So first, let's see the Meissner effect. So first, let us take the derivative of free energy with respect to the vector potential. Then we can derive this equation. Here J is the current of the system, and the A is the vector potential. And combining this equation and the Maxwell's equation, then we can derive the so-called London equation. And if we solve this equation, then we can obtain this solution, which tells us that magnetic field cannot survive or penetrate into the samples. So external magnetic fields penetrates only over the penetration depth lambda. So this is a very important length scale of the superconductivity. And in fact, there is one more important length scale, which is called coherence length. So here, let us consider to introduce phase modulation to the order parameters. So usually the Cooper pair is a pair of electrons having the momentum k and minus k. So the momentum of Cooper pair is in total 0. But if we introduce the external field, or if we make an interface between superconducting states and the normal state, sometimes Cooper pair has a finite momentum. So it's a pair of minus k and k plus q. And in such a situation, we have a phase factor, exponential IQR. And then if there is such a phase modulation, then on top of the second order terms and fourth order terms, we have gradient terms, contribution of gradient terms. And that makes free energy higher. That means it's not stable. So the amplitude of order parameter becomes small. And if we plot psi q as a function of q, then the size of the amplitude becomes smaller and smaller, and eventually it becomes 0. So if we introduce too large q, the superconductivity disappears. And from this curve, we can introduce one more length scale, xi, coherence length, which represent how rigid the order parameter is. And in fact, this length scale is closely related with the size of a Cooper pair. So this is the second important length scale of superconductivity. And in fact, so if there are two types of superconductors, and the characteristic features of these two types of superconductors can be discussed by the ratio of the magnetic penetration depth lambda and the coherence length xi. So there are two cases. So one is xi, the size of Cooper pair is very large, but the length scale of penetration depth is very short. And this is type 1 superconductor. And the type 2 superconductor is opposite. So the size of Cooper pair is small, but penetration depth is large. And so these two superconductors have a very different phase diagram. So first, let's see the case of type 1. In the case of type 1, in the plane of magnetic field and temperature, there are only two phases, normal state and superconducting state. And in the superconducting state, so the size of Cooper pair is large, and the penetration depth is very short. So in general, so essentially, magnetic field, external magnetic field, cannot penetrate into the samples. So in the sample, basically, the magnetic field is 0. But on the other hand, in the case of type 2 superconductors, the size of Cooper pair is small, but the penetration depth is large. So magnetic field has a chance to penetrate into the sample. So it makes the vortex. So in the case of type 2 superconductors, on top of the phase of normal state and Meissner state, between these two states, we have the so-called vortex state. And this is an experimental visualization of vortex. Okay, and so if we know the values of xi and lambda, and we know the ratio between these two parameters, length scale, then the characteristic features of superconducting states can be predicted. So these two parameters are very important. And in fact, if we know the values of Tc and Xi and lambda, then we can also predict the phase diagram, especially the limit of the superconducting state. Critical magnetic field, critical current density, and critical temperature. And so let us first look at the axis of current and discuss the depairing current density. So we start with the Ginzburg-Landau free energy. And as I mentioned, if we take the derivative of free energy with respect to vector potential A, then we can obtain J current. And this current, we can see that it's proportional to Q. Namely, when the momentum of Cooper pair is 0, then the J is 0. And by introducing momentum, then J becomes larger and larger. But if we introduce too large Q, then superconductivity will be destroyed. So it becomes small again. So it takes the maximum between this 0 and the limit of Q. And so this the maximum value is the so-called depairing current. And in a superconductors, we cannot introduce current larger than J depairing dp. And so this depairing current is an theoretical upper limit of critical current J. So usually JC is much smaller than JDP, and the JDP gives an upper limit, theoretical upper limit of JC. And so this JDP is related with, So from this equation, if we know the value of lambda and Xi, and psi 0 is a flux quantum, so it's just constant. So if we know the values of lambda and Xi, then we can estimate JDP. So we see that Xi and lambda is very important quantity. And next, let us move on to the axis of the magnetic field here. And let's think about the case of type 2 superconductor, and assume that we introduce very large magnetic field, and the order parameter psi q becomes sufficiently small. And then in the Ginzburg-Landau free energy, we can forget about fourth order terms, and then we can derive the linearized Ginzburg-Landau equations for psi, whose form is exactly the same as harmonic oscillator, Schrödinger equations of harmonic oscillator. And for the Schrödinger equations for harmonic oscillator, we know that the minimum eigenenergy is half h bar omega. So the energy must be larger than half h bar omega. And from this equation condition, we can say that to obtain the superconducting solutions, magnetic field must be smaller than hc2. So hc2 is given by psi 0 over 2 pi Xi squared. So if we know the values of coherence length, then we can we know the critical magnetic field. So so we can see that we have seen that so if we know, we can estimate non-empirically the values of Tc and Xi and lambda, so these three key quantities. Then we can discuss or predict the physical properties of superconducting state in this region, or the phase diagram, especially the limit of magnetic field or temperature or current density. So, this argument tells us that the importance of ab initio, non-empirical calculation of these three quantities. And then, so here let me emphasize the importance of ab initio calculations again here. So as I mentioned, first principles calculation can play a crucial role in predicting superconducting properties and guiding the theoretical design of new materials. And this role is particularly significant for superconductors and extreme conditions for which experimental measurements of these key quantities are challenging. And in fact, especially so superconductors and extreme conditions. The role of the fact that the role of ab initio calculation becomes important has been demonstrated by the studies of hydrogen sulfide. And so for this compound, in 2015, the group of Michael Elements, so they reported that when we applied extremely high pressure, higher than 100 gigapascal, and then we can observe the superconducting transitions at very high temperature. So the maximum value is 200 Kelvin, which was the record of highest TC. But it should be noted that, so this is a very interesting and a remarkable experimental discovery. But here I'd like to note that just 5 weeks before this experimental report, Duan and others posted a paper concluding that, so predicting that when we applied very high pressure, like here, then the hydrogen sulfide becomes 83S, whose crystal structure is shown here. And it is very good for superconductivity. So this paper indicates that the important role of ab initio calculations. And from now, I'm going to discuss so how to estimate or evaluate the three key quantities of superconductivity without referring to the experiment data. So transition temperature Tc, and coherence length, and magnetic penetration depth. Okay, so the first, formulations. And regarding the non-empirical calculation of materials, and one of the most widely used and established approach is that based on density functional theory, formulated by Hohenberg-Kohn or Kohn-Sham. So in this framework, we start with the so-called Hohenberg-Kohn theorem, which guarantees the one-to-one correspondence between the external potential, or the potential made by atoms, and the density of the ground state. And in the class of exercise class of quantum mechanics, students usually solve the Schrödinger equations for given potential and calculate the wave function of the ground state and calculate the density of the ground state. But this theorem guarantees that So if some potential, if some the density is given, then uniquely we can identify the potential for which this given density becomes the density of the ground state. And once V is determined, then Hamiltonian is determined. So not only the ground state, but also the excited state is determined. So the response of the system is also determined. So the information of the density of the ground state is very important. And to obtain the density of the ground state, actually we can obtain it by solving the Kohn-Sham equation. So we map the original many-body system to the auxiliary effective one-body system. And by solving the one-body Hamiltonian, we can obtain the density of the original many-body system. And so we have to solve this equation self-consistently, this Kohn-Sham equation. And this framework can be extended to a superconducting state. And so in this framework formulated by Hardy-Gross and his collaborators, we introduce two types of potential, the normal density and the anomalous density, all the parameter of superconducting states. And we introduce two types of potential. There's a normal external potential and the pair field. So one-to-one correspond to between two types of potential and two types of density. And the Kohn-Sham equation becomes a Kohn-Sham-Bogoliub-Dojan equation. So this is the standard Kohn-Sham equation, but in the Kohn-Sham-Bogoliub-Dojan equation, we have to solve these two equations. And if we solve these two equations self-consistently, and then we can obtain two types of potential and two types of density. And so from this Bogoliub-Dojan equation, we can derive the so-called gap equation. So in a superconducting state, at the Fermi level, so we have a gap, superconducting gap, which is closely related with all the parameter psi. And so this is an equation to determine the size of gap for given temperature. The beta is the inverse of temperature. Yeah. And the Xi is a Kohn-Sham energy. And this F is a kernel of this gap equation. And so we have two contributions, EH and FXC. And the EH is Hartley contributions, whose form is well known. But the problem is this exchange correlation function F. And so there should be a very universal exchange correlation function which can be applied to any superconductors. But unfortunately, we do not know the exact form of this FXC. But for conventional superconductors mediated by phonons, we already know the form of exchange correlation functional. And it has been shown that if we consider the three effects, then we can obtain TC, which reproduces the experimental value quite accurately. So the first effect is the so-called mass enhancement effect. So when the electrons and the phonons are coupled, and then due to this coupling, the effective mass of the electrons becomes heavy. And so this the first term represent this effect. And the second term is phonon-mediated attractive interactions. So as I mentioned, a phonon can induce an effective attractive interaction between two electrons. And the third one is the Coulomb repulsion. So in materials, two electrons have Coulomb repulsions. And if we introduce these three terms, then we can calculate superconducting transition temperature quite accurately. And the reason why we can calculate DC quite accurately is that density functional theory for conventional superconductors, we can calculate phonon properties quite accurately. And so one approach is density functional perturbation theory. So when we calculate the phonon-mediated superconductivity, we calculate the coupling between electron and phonons, and so this matrix element. If the ions makes the perfect lattice and doesn't move, then Bloch wave with momentum k does not have a matrix element with the Bloch wave with k plus q. But if the position of atom moves and there is an atomic displacement u, and potential changes, and then the Bloch wave with momentum k will be scattered to k plus q, and so this matrix element becomes finite. And for phonon frequencies, we can obtain it in the harmonic approximation by taking second derivative of the total energy E. And so we need to calculate so this derivative with respect to u. But in density functional theory, all physical quantities are the functional of density of the ground state. So if we know the response of the density of the ground state against the atomic displacement, then using this chain rule, we can calculate this derivative. And this strategy works quite successfully. And so this is the result of calculation for aluminum and lead and niobium. And the solid line is the theoretical result, and the dotted line is the small circles or squares are the results of experiment. And we see that the agreement between theory and experiments are very good. So we can construct these three factors, and then so this is the benchmark calculation for aluminum and niobium, and so here I plotted the size of gap function as a function of temperature, and so we see that so in the case of niobium, it becomes 0 at around 10 Kelvin, and aluminum at 1 Kelvin. And in both cases, the agreement between theory and experiment is very good. So then let us move on to the calculation of Xi and lambda. And so as I mentioned, so for Xi and lambda, so we introduce a phase factor in our order parameter. And so in superconducting density functional theory, this situation can be realized by introducing a phase shift. And so I'm not going to the details, but we can derive the gap equation for pairing with finite momentum. And by solving this equation, we can plot all the parameters as a function of q. And by looking at how quickly it decays as a function of q, we can estimate this Xi, the coherence length. And also we can calculate the current J. And by looking at the slope of J as a function of Q, or by looking at the maximum value, differing current J dp, we can estimate the magnetic penetration depth. So this is the formulation, how to calculate Tc and Xi and lambda. So let us move on to the results. Okay, so this is the results for niobium first. And so this is a plot of the gap function or all the parameters as a function of wave number Q for a variety of temperatures. At low temperatures, the psi is large, and higher temperature, it becomes smaller and smaller. And this is a plot of current. So it takes a maximum and then becomes smaller. So this maximum value corresponds to the JDQ. And this is the result. So critical temperature and coherence length and magnet penetration depth. And we see that agreement between theory and experiments are all good. So the experimental measurements of lambda is actually a bit difficult, more difficult than Xi. So depending on the literatures, there are some ambiguities, but I would say that the agreement between theory and experiment is good. And importantly, from this result, we can say that so lambda is larger than Xi. So niobium should be type 2 superconductor. So it's consistent with the experiment, and so it should be noted that so without referring to the experiment data, we can say that we can predict that niobium is type 2 superconductors from this calculation. And this is the results of aluminum. And the calculation of aluminum is a bit difficult because Tc is a bit low. So energy scale is very small. But so in our calculation, transition temperature is a bit overestimated, and Xi is underestimated by a factor of 2. But our agreement between theory and experiment is good for lambda, magnetic penetration depth. And in this case, so lambda is an order of smaller than 100 nanometers, but Xi is larger than 100 nanometers. So we can safely conclude that aluminum is type 1 superconductor. And this is also consistent with experiment. And the next is 83S. So this is an result of, I forgot the pressure, but I think it's about 150 gigapascal. And so this is a result of transition temperature. The agreement is good. And for coherence length, so HC2 is not experimentally determined, but by looking at the slope at high temperature and extrapolate into the zero temperature, we can roughly estimate that HC2 is about 80 Tesla. And from this number, we can roughly estimate the Xi as large as 2.0. And this is consistent with our theoretical values. And regarding the magnetic penetration depth, as far as I know, so experimentally, this quantity is not yet determined. But according to our calculation, it should be 30 or 40 nanometers. And interestingly, the number of JDP, differing current, is extremely large in this case. And so we perform this calculation for a variety of elemental materials or compounds. And the blue shaded materials are type 2 superconductors. And so concerning this large number, so if we compare the H3s with high TC cuplets. And then in the case of high TC cuplets, the coherence length is about 3 nanometers. And it is almost the same as H3s. But lambda is about 300 nanometers, which is larger than H3s. So from this equation, so Guzai is similar, but lambda is larger in cuplets. That means JDP should be smaller than H3s. In other words, H3s, the depairing current is expected to be larger than that of cuplets. So this is a theoretical result. Okay, so finally, I would like to discuss the future perspectives quite briefly. So in the first part, I mentioned that in this plot, we have a variety of superconductors. And today, I focused on conventional superconductors. But in this plot, we have many interesting high TC unconventional superconductors. And then the question is whether we can apply this formalism to the unconventional superconductors. But here we should note that we have to be careful that in DFT calculation, so we start with the DFT calculation, but in DFT calculations, we employed the so-called local density approximation, LDA. But this approach sometimes doesn't work. And the famous example is on the cuplet. And the mother compound of cuplet is a Mott insulator, but Mott insulator cannot be described by LDA. So to describe such a non-trivial state, we have to go beyond LDA. And so one promising approach is combining LDA with an accurate many-body approach. And dynamical mean field theory and DMFT is one of the promising approach. And the people in the Flatiron Institute, the Center for Computational Quantum Physics, people are studying this problem intensively and extensively. And we also performed such a calculation for one unconventional superconductor, alkali doped fluoride. It's a molecular solid. And among molecular solids, this compound has the highest TC. And this is the phase diagram in the plane of temperature and so volume of the unit cell. Volume of unit cell means, roughly speaking, it's a pressure. So PT phase diagram. And we have a Mott insulating phase. So LDA cannot describe this phase diagram. But if we perform LDA plus DMFT, then we can reproduce the superconducting phase or Mott insulating phase. So, and recently we perform a calculation to estimate coherence length and penetration depths, and these are results. And for Guzai, I would say that the agreement is good. And for penetration depths, given that experimental determination is a bit difficult, so I would say that the agreement is not so bad. But anyway, so the calculation of Guzai lambda in unconventional superconductors is an interesting future problem. Okay, so let me summarize my presentation today. So I first show that the first principles calculation plays a crucial role in predicting superconducting properties and guiding the theoretical design of new materials. And this role is particularly significant for superconductors under extreme conditions because experimental measurements of key quantities become difficult. And for conventional superconductors, it seems that Guzai and lambda and TC calculation of these three quantities becomes possible. And developing a methodology for unconventional superconductors is an interesting challenge in the future. Okay, so let me finally acknowledge my collaborators, especially Mitsuaki Kawamura and Takuya Nomoto and Nicholas Witt, and also Yusuke Nomura, Sergei Brenner, Tim Wehling, and Sasha Lichtenstein. And I'd like to thank the financial support from Ministry of Education, Japan. Thank you very much for your attention.
Thank you for the interesting talk. We have some time for questions, and please, if you ask a question, use the seat microphone.
There were reports of room temperature superconductor from Korea. I'm not sure what the status is. I think this may have been found incorrect by other groups, but I'm curious if the numerical methods that you're using here can perhaps, you think, identify some room temperature superconductor via a numerical scan, so from theory.
So in my opinion, the so-called LK99, the room temperature superconductors discovered in Korea, I think it's not correct. And if we look at the electronic structure, the bandwidth is around the film level. It's very, very narrow. And so energy scales of the kinetic energy of electrons is too small to realize high TC or room temperature superconductivity. So, but on the other hand, so we have not yet performed such a calculation, but in principle, we can perform high throughput calculation of this SCDFT method. And I expect that we have a chance to find high TC superconductor, or more importantly, large JC superconductor. So in my opinion, not only TC, JC is a very important quantity. And finding superconductors having large JC is a very important problem and important challenge. Yes.
Other questions?
About the JC, actually, can you comment on what would be, the minimal JC required for applications, or what?
Minimal JC.
Yeah, what's the target JC for applications? Let's say.
Yeah. So when we think about an application of superconductivity, so we usually introduce current. So if the current JC is too small, then even though TC is high, basically it is useless. So the evaluation of JC is very important. That is, I think, yes. Phase diagram. And yeah, so it should be noted that in this presentation, I discussed the differing current density. This is a theoretical upper limit of JC. So in reality, so if we introduce current, then we have magnetic field that makes vortex. And if there is no defect or grain boundary, and then if there is no pinning of vortex, then vortex flows in a sample. That makes a resistivity. And so to have a large enough current, those vortex must be pinned or fixed. And this differing current, so we assume that the vortex doesn't move. So the precise estimation of this JC, we have to study the pinning of vortex. And that is also a very important future problem, ab initio calculation of vortex pinning.
One perhaps higher level, To what extent can density functional, superconducting density functional theory be used in the context of high throughput materials search? And what have been the successes? And perhaps a more technical question. So in, conventional theories of Migdal and extensions, theory of Migdal-Ashberg and extensions, there is the infamous parameter mu star, which is the Coulomb pseudopotential. Can the use of density functional, superconducting density functional theory shed light on what the correct value of mu star actually is?
Regarding the second question, in the framework of SCDFT, we do not introduce the pseudo-Coulomb potential.
I know.
Because this equation is basically these quantities are all static. So maybe you may think that the so-called retardation effect cannot be described in these equations, but there is an quantum orbital dependence. So quantum state dependence of kph and kc is very different. So without introducing mu star, we can describe the retardation effect effectively. And the numerical cost to solve this gap equation is much cheaper than the standard Migdal-Ashberg equation, because there is no frequency in the equation. And so that is a good thing when we think about performing a high throughput calculation. And in fact, my collaborator, Mitsuaki Kawamura, so he performed the high throughput calculation for elemental metal, and he made a list of possible calculated TC and compared the theoretical TC and experiment, and the agreement between theory and experiments are basically very good.
So maybe time for one more question.
So how does quantum geometry, about which we've been hearing a lot, fit into this?
Quantum geometry becomes important in many band systems, and that effect can be very interesting when the characters of band is very different. But unfortunately, in the current formalisms, we start with a single component Ginzburg-Landau theory. So the multi-component version of Ginzburg-Landau theory is a very important future problem.